Hi, this is the lecture for section 2.2, and we're going to talk about general solutions of linear equations. So a general linear equation in this, oh, I just noticed a slight typo. Let me just fix that. Okay, fixed. All right, so yeah, I was just missing this of x term here. So this is a general linear nth order differential equation. So it's linear in the dependent variables. The y is the dependent variable and its derivatives. So y prime up to the n minus first derivative of y, and this is the nth derivative of y. So this is like a general linear nth order differential equation where we're assuming that this leading coefficient is 1. So if it's not, then you can divide by whatever this is, assuming this thing is not 0 at well, maybe it will be 0 in certain places, so you have to worry about that. But yeah, this is the general form that we're interested in. And we're going to talk about today the method for solving such linear equations. So the method to solve this is really a two-part method. So the first part is that we need to find what's called the complementary solution. So the complementary solution is a solution of this form. So it's a linear combination of these functions y1 up to yn. So that's a linear combination. So our complementary solution is built up of these y1 up to yn functions. And this is our, under certain conditions like linear independence, this is a general solution of the homogeneous equation. So the homogeneous equation is the same as the original equation, except now we have a 0 here. So that's the only difference. So if you look up here, we have a function f of x on the right-hand side. And in the homogeneous equation, we just replace that with 0. So we need to find our general solution for this homogeneous equation. And this is referred to as the complementary solution. And once we have this general solution for the homogeneous equation, then all we need to solve our differential equation is just a single particular solution of the equation. And so once we have just a single particular solution, then a general solution of the differential equation is going to be, we take our complementary solution and we take our particular solution and we add them together. And this will give us a general solution for the differential equation. So let's have a look at this on an example. So we have an initial value problem right here. So there's the differential equation. So it's a linear differential equation. And we have, because it's a second order differential equation, we need to have two initial conditions. We need to have like an initial position and initial velocity, if you want to think of it that way. And we're told that the complementary solution is this one. And it's pretty easy to check that cosine x is a solution for the homogeneous equation, where we put a 0 here. So cosine x will satisfy y double prime plus y equals 0 if y is equal to cosine x. And if y is equal to sine x, also we get y double prime plus y equals 0. So these are both solutions of the homogeneous equation, and we just form a linear combination of them, and that gives us a general solution for this homogeneous equation. Okay, and a particular solution is this one, 3x. So we can check that if we take the derivative of 3x twice, then we get 0. So the first derivative is 3. The second derivative is 0. So we would get 0 plus 3x. Yep, and that equals 3x. So that is definitely a particular solution of the differential equation. And so now we know what the general solution of this differential equation is. So what is the general solution? Or maybe it's better to say a general solution, because you can have you could have slightly different forms of the general solution. But it is a general solution of this differential equation is y equals c1 cosine x plus c2 sine x plus 3x. So that is our general solution for this differential equation. So we have the complementary solution, which is the general solution of the homogeneous equation, and we have our particular solution right here, and that is just a single solution that satisfies the differential equation. But notice what's important about this particular solution is it doesn't need to satisfy these initial conditions. That's what this complementary solution is for. So these initial conditions are going to be used to determine these constants here. And in that way, we're able to get a solution of this differential equation that satisfies these initial conditions. So let's do that right now. So the initial conditions are y of 0 equals 2. So what do we get if we plug in 0? We'll get c1 times cosine 0, which is 1, plus c2 times sine of 0, that is 0. Oops, I almost forgot the 3x, plus 3 times 0, and that equals 2. Okay, and that tells us that c1 is equal to 2. Okay, and now y prime of 0, this is equal to minus 2. Oh, let's take the derivative of this before we do that, just to be a little bit better organized. So y prime is equal to negative c1 sine x plus c2 cosine x plus 3. Okay, so that's just the derivative, and now we can use that here. So we get negative c1 times 0 plus c2 times 1 plus 3 equals negative 2. Okay, so c1 plus 3 equals negative 2. That means c2 is equal to negative 5. Okay. So therefore, the solution of the initial value problem is y equals 2 cosine x minus 5 sine x plus 3x. Okay, so hopefully that makes sense. So this is an example of what happened, what you need to do once you have the complementary solution. So once you have this complementary solution, and once you have this particular solution. Oops. So once we have those two solutions, then we are able to find the solution to the initial value problem and by satisfying these initial conditions. Okay, so now the question is comes to how do we find this complementary solution, and how do we find this particular solution? So that's the direction we're going in now in this chapter. We're going to look at a variety of methods for finding this complementary solution and methods for finding this particular solution. And then after you have that, you just combine them together and determine the unknowns C1 and C2 that satisfy the initial conditions. Okay. So an important thing that I mentioned when we're starting out is that the functions in the complementary solution, they need to be linearly independent. So well, we've already seen that if you have a function in there that is redundant, right? So in other words, it depends linearly on the other functions, then it doesn't add anything to your complementary solution. We might as well throw it out because it's redundant. So the important thing that we need in order to be able to satisfy any initial condition that we need to be able to have a full set of linearly independent solutions. So a full set of non-redundant solutions. So let me just mention that. So what this means is, in other words, no redundant solutions. So we don't want any redundant solutions. That's what this linear independence is about. Okay. So these are all going to be solutions. So y1 up to yn are going to be solutions for this homogeneous equation. So we've talked a little bit about how to determine if functions are linearly dependent with two functions. We did that last section. So how do we do this when we have like n functions, like when we have more than two? So it's very much the same as we had before. So we just extend this idea to n functions. So we say that the n functions f1 through fn are linearly dependent. In other words, there's some redundant function in there. If there are scalars, c1 up to cn, and the important thing is that they're not all zero, so that's the important thing, such that this linear combination of these functions is equal to 0 for all x. Okay, so if we can find some scalars that are not all 0, such that this linear combination is equal to 0 for all x, then we've got linearly dependent functions. And that means at least one of the functions is redundant. We may have more than one function that's redundant, but we do have at least one that's redundant. So we could throw it out. We don't need it. Okay. So what does that mean? So what is the definition for linear independence? So in other words, no redundancy. So some functions are linearly independent if, whenever we form this linear combination of the functions, the only way that it can be equal to 0 for all x is that all of the coefficients c1 up to cn are all 0. So if this equation implies that all of these coefficients are 0, then we've got linear independence, and we're happy because that means there's no redundant function in this set of functions. Okay. So let's do an example now that we've seen this definition for more than two functions. So let's start with three functions. So we have these three functions, and we want to show that they are actually linearly dependent by finding C1, C2, C3 not all 0, so that this linear combination of the functions is equal to 0 for all x. And that's the idea. And you can kind of see that this function seems to be built up of, some of this function and some of this function. And that's what gives us this guy. So this guy definitely looks like the redundant function, but so one of these, at least one of these functions is redundant, so we could throw it out. Okay, so let's see how to do this. Okay, so first of all, we're going to set up this equation, C1 f1 of x plus C2 f2 of x plus C3 f3 of x equals 0. So that is C1 times 2x plus C2 times 3x squared plus C3 times 5x minus 8x squared is equal to 0. And this is an equation that's true for all x. So, and we want to see if we can find some non-zero C1, C2, C3 so that this is equal to 0 for all x. Okay. So I suppose we could kind of guess our way to find such a solution. But let's see, what are some other ways that we could do this? So we know it's true for all x, so we could substitute different values of x into this equation. But I don't know, so let's start. Let's start to rearrange this maybe a little bit. That might be a good place to start. So let's see. I have some linear terms here. So there's an x and an x here. So let's combine those together. And then there's x squared terms here. So I'll combine those together as well. So the x terms, we have a 2c1 plus 5c3 times x. And then we have 3c2 minus 8c3 x squared, and that is equal to 0 for all x. Now, if you know something about polynomials, you'll know that the only way for a polynomial to be equal 0 everywhere is for its coefficients to be equal to 0. So in fact, that's because these two functions, x and x squared, are linearly independent. And so the only way to have this equation be true for all x is for this coefficient and this coefficient to be equal to 0. So that's one approach. And then another approach, of course, is to just plug in different values of x into here and here. And I think that's probably a little bit more convincing because do we know already that x and x squared are linearly independent? I don't recall if we did precisely that example last time. So just trying to think if we could go that route. But let's go a simpler route. So we could maybe show that x and x squared are linearly independent, and then we could immediately write. Well, let me do both. So let's do both. So note x and x squared are linearly independent. We could maybe do like a Wronskian type approach to show that. So because if they're linearly dependent, then the Wronskian has to be 0 everywhere. So I guess we could like form the Wronskian of these two functions, x squared, then we take the derivatives like this. And then we know how to do this determinant. It's 2x squared. So you do x times this minus this times that. So we get 2x squared minus, 2x squared minus x squared, and that is equal to x squared. And since this is, which is not zero everywhere, right? It is 0 when x is 0, but it's not 0 everywhere. And the only way for the so if these functions are linearly dependent, then the Wronskian has to be 0 everywhere. So this shows that these two functions are linearly independent. Okay, so that's sort of that argument. And so therefore, that means that the only way for this to be equal to 0 is for these two coefficients to both be 0. And so we get 2c1 plus 5c3 is equal to 0. And we get 2c2 minus 8c3 is equal to 0. Okay. So there's some linear algebra techniques that we can use to find all the possible solutions of these two equations. But all we really need is to find a single non-zero solution. And what these two equations tell us is that we can just substitute, say, a value for C3, and then we can solve for C1 and C2. So let's take C3 to be equal to 1. That's a good value. So then 2c1 plus 5 is equal to 0, and 3c2 minus 8 is equal to 0. So therefore, we would get c1 is equal to negative 5 over 2, and c2 is equal to 8 over 3. So clearly, this is a non-zero set of values that would work. So that would definitely work. So those values of C1, C2, C3, they're clearly not all 0. In fact, all of them are non-zero. And we're able to satisfy this equation that way. So that's a pretty good way to do this. I guess let's just explore quickly this other approach that I proposed. So let's have a look again at this equation. So if you're not feeling so great about that Wronskian argument, here's another approach. So this has to be true for all x. So we could plug x equals 1 into it, and we would get 2c1 plus 5c3 times 1 plus 3c2 minus 8c3 times 1 equals 0. So I guess I'll put the times 1 times 1. And what does that give us? So that gives us 2c1 plus 3c2 minus 3c3 is equal to 0. So that's one equation. And then we could plug in another value for this x. So minus 1. So we'll get 2c1 plus 5c3 times minus 1 plus 3c2 minus 8c3 times 1. So minus 1 squared is 1. That equals 0. And in this case, we get 3c2 minus c1. So that's c1. And then we get, oh, whoops, I made a mistake there. That is a c2 and that's a c1. So we get negative 2c1 plus 3c2. And then minus 13c3 equals 0. Okay, so now we get these two equations here. We get this equation and this equation. Okay, so this is turning out to be a little bit more complicated, so probably many of you are thinking, I prefer the first method, it seems easier. But we could still do a similar trick. I'm just checking that it's still recording. Yeah, okay. So we could still do a similar trick where we just substitute a value for one of the three variables into these equations and then solve for the other two variables. So again, we could just say, well, let's just take C3 to be equal to 1. I don't know why we would choose that. I guess you could choose any of the variables to be 1 and then solve for the other two. But yeah, let's do the same one and see if we get the same answer. So if C1, so let's write it this way. So we're going to take C3 to be 1. That's what we did before, right? Take C3 to be 1. And then what do we get? We get 2C1 plus 3C2. And then this will be minus 3. So I'll just move that to the other side. So we'll get that is equal to 3. And then on the other equation, we get negative 2C1 plus 3C2. And that will be equal to 13. Now we have these two equations with two unknowns, and we can combine them together to get rid of one of the variables. So let's add these two equations together, and the 2C1 minus 2C2, that equals 0. So we'll get 0 here plus 6C2 is equal to 16. And that tells me that C2 is equal to 16 divided by 6, which is 8 divided by 3. I believe that's the answer we had above, right? 8? Yes, C2 is 8 divided by 3. Okay, so we're getting the same answer with this technique. And therefore, so that implies that 2C1 plus 3 times 8 over 3 is equal to 3. So we get 2C1 plus 8 equals 3. And so therefore, C1 is equal to, well, let me do it in two steps. 2C1 is equal to minus 5, and therefore C1 is equal to negative 5 over 2. Okay, so there's our answers. And I think that was the same. So negative 5 over 2. Yes, so we got the same answers, right? Negative 5 over 2 and 8 over 3. Let me highlight this stuff. So there's our initial non-zero solution showing that they're linearly dependent. And then we did this other technique and we ended up getting precisely the same values. Okay. So either way, we've shown that those functions are linearly dependent. Okay. All right, so I think that was probably a good example to look at because we got to see how to use the Wronskian to show x and x squared were linearly independent. So let's generalize this idea. So how can we use the Wronskian to prove linear independence for not just two functions, but for n functions? So again, this is just repeating the definition of linear dependence of a set of functions. And what does this tell us? If we have this equation equals 0 for all x. Well, here's a trick we could do. So if this is really true, then we could take the derivative of both sides of this equation, and we will get this. So because it's true for all x, we know that if we take the derivative of the left-hand side, which is going to be equal to this, that also has to be 0 for all x as well. Okay, and we could take the derivative again, because this was true for all x, we can take the derivative again, and we get another equation that is going to be true for all x as well. And so on. We can do this, n minus 1 times, and we'll end up getting these n equations. So 1, 2, 3, all the way up to n. So we get n equations here. They're all equal to 0 for all x. Okay, so what does this mean? So here we have n linear equations in the C1 up to Cn. So C1 up to Cn are kind of like our unknowns, and we have n equations for these linear equations. And we know that there are scalars C1 up to Cn that are not all 0. So that means we actually have a solution to this set of equations here that is not all 0. And what does that mean? So in linear algebra, what that tells us is that if you have a linear system that has the trivial all 0 solution, right? So we could put zeros through all here, we get 0. We could put zeros here. So if we just substitute zeros in, that's obviously a solution. But we also know that we have another solution which is not all 0. So the only way for a linear system to have two different solutions like this is if the determinant of the coefficient matrix is 0. So that's what it means. So anytime you have a linear system, it doesn't have to be like the all 0, like a homogeneous linear system, like where the right-hand side is all 0. If you have any linear system in n equations, n variables, and you have more than one solution to that linear system, that immediately tells you that the determinant of the coefficient matrix is 0. So let's use this and let's see what is the determinant of this coefficient matrix. So here it is. So this is the coefficient matrix here. The first equation, these are the coefficients of the C1 up to Cn. The second equation had these as the coefficients of C1 up to Cn. And the last equation had these coefficients from C1 up to Cn. And so this is our n by n matrix, and we want to take the determinant of it. So that's what these vertical lines mean. Take the determinant of that matrix. That's what we call the Wronskian of f. And if these functions are linearly dependent, then that Wronskian has to be 0 for all x, right? So that example we saw above, we did the Wronskian of x and x squared, and we found that sometimes it was not 0. And therefore we know immediately it's not this situation here. So this situation is not happening. And that means that we must be linearly independent, because if we were linearly dependent, it would always be 0, and that didn't happen. So this is the idea for more than two functions, and it gives us this really nice linear independence test. If the Wronskian is not 0 for some value of x, right? It doesn't have to be for all. So our Wronskian above, we found it was x squared. So if x is 0, then it's 0, but if x is 1, then it's not 0. So that's a value of x where the Wronskian was not 0 at that value of x. And if that happens, then the functions are linearly independent. So it's a really nice, clean way to, well, it's like a very systematic way to show functions are linearly independent. Just write down the Wronskian, figure out its determinant. Is it non-zero sometimes? Yes, linearly independent. Very nice. It's almost like less work than finding these functions are linearly dependent, right? That was a lot of work in that last example. So this is going to be less work. I mean, there's some work involved. You have to compute these derivatives, and you have to compute this determinant. So there's some work involved there. Okay. So let's look at an example. Okay, so this is going to generalize nicely what we saw above. So above, we know that these two functions are linearly independent. And what if we add this function in? Are they still linearly independent? The answer is yes. So we're just going to show that these functions are linearly independent using the Wronskian linear independence test. So let's start. So the Wronskian of these three functions is going to be the determinant. So the first row are just those functions, and then we take the derivatives of the functions. So we get 0, we get 1, and this is 2x, and then we have 0, and this is 0, and this is 2. Okay, so we're going to determine what is the value of this determinant. So we need to remind ourselves, how do we find the determinant of a 3x3 matrix? So 2x2, we saw it was easy. There's an easy formula for that. But if it's a 3x3, then what do we do? So we have to use a technique called cofactor expansion. So the first thing to note about cofactor expansion is that there's an associated plus minus pattern to this determinant. So it always starts with plus, and then it just alternates minus plus. So then it's just like a checkerboard. So just like a checker or a chessboard, you have alternating plus minus pattern. And we're going to need to know this plus minus pattern in order to determine to get the determinant. Okay. So how do we do this? So we have a choice, actually. We can either expand this determinant along any row. So we could use this row to expand to do the cofactor expansion, or we could use this row, or we could use this row. So we have a choice. Any of these rows we could use. We could also use a column. So we could expand using this column, or we could use the second column, or we could use the third column. Now, a general rule when choosing which row or column to use, you're going to get the same answer no matter what. But it's often a lot easier if you use a row or column that has a lot of zeros in it. And we'll see why that is the case. But for now, let's start with just using the first row, and then maybe we'll use a different row or column. Maybe we'll use this first column as because that looks pretty easy to use that one. But let's start by using this first row. Okay. So let me highlight that row. So we're going to use this row here as the row that we're going to use for expanding, doing our cofactor expansion. So the idea is that we have 1 times, and then there's a determinant of a 2x2 matrix. I'll explain what that is in a second. But importantly, this is a +1, and that comes from this sign pattern of this 3x3. And then we do minus, because the next sign is minus, x times a 2x2 matrix determinant. And then we have plus x squared times a 2x2 determinant. Okay, so we still have to figure out what this is. So I'll just put these dots in here for now to indicate that these are 2x2 determinants, and we'll just have to fill those in a second. And just in case we need more space, let me just move this over here. Okay, so And just to highlight, we used plus minus plus here because of the sign pattern. Okay, and then we used 1x squared. That's from this first row. Okay, so now what are these here? So these 2 by 2 matrices are obtained as follows. So what we'll do is we're going to be looking at this 1, and we're going to just scratch out the first row and column. So this is in the first row and column, so we'll scratch out this row and this column, and that leaves us with this 2 by 2 matrix right there, and that is what goes in here. So this is 1, 2x, 0, 2. And then we do the same thing here for the next entry. So x is in the first row and this middle column. So we'll scratch out this row and this column, and we're left with 0, 0, 2x, and 2. So that's what goes here. So 0, 0, 2x, and 2. And then finally, this x squared, it's in the first row and the last column. And so once we delete those, we're left with this matrix, 0, 1, 0, 0. 0, 1, 0, 0. Okay. So now we just have to compute these 2 by 2 determinants. So we know how to do this. So it's 1 times 2 minus 0 times 2x. Then minus x, 0 times 2 minus 0 times 2x. And then we have plus x squared times 0 minus 0 times 1. And we end up getting, let's see, so this will be 0, that's 0, so those go away, and here we're just left, so this is 0 here, so we're just left with 1 times 1 times 2, so that is 2. Okay, so that is the Wronskian, and since it is not 0 for some value of x, in fact it's not 0 for, well, it's just not 0. So it's not 0 no matter what x is. So that is not 0. So therefore, 1x and x squared are linearly independent. Okay. So let's just quickly go through that example again with this Wronskian, and I'll show you why it's nice to expand over a different row or column. So let me copy this, and we'll do this again. Okay, so now I think a good one to use is maybe the first column here. So that'll be nice. So we'll use this column, and we'll do the cofactor expansion. So we're going to get plus 1, so that's plus 1, times the determinant of, and then if you delete the first row and column, we're left with this 2 by 2 matrix. And then we're going to get minus 0 times the determinant, but it's going to be minus 0 times that, and then we'll have a plus 0. So that makes our lives a lot easier. We don't have to compute as many determinants, and we end up getting 1 times 2 minus 0 times 2x, and that is 2. So that's a little bit easier way to do it, is to look for a row or column that has a lot of zeros in it, and then your life is a lot easier that way. Okay, so, and you may actually know of another way to do a 3 by 3 determinant. There is another trick to doing a 3 by 3 determinant Maybe I'll review this here. So note, and this will only work for 3 by 3. So another way to compute 3 by 3 determinant is like this. So imagine we have A, B, C, D, D, E, F, G, H, I. So what is this? What is this determinant? Well, what we can do is just trying to see what is a good way to do this. So essentially, let me just repeat this down here. So I'm going to copy this, paste it right there. So what you can do is take the first 2 columns here and you just repeat them over here. So I'm going to also copy this, paste it there, and then I'm going to look at some diagonals here. So there's going to be these 3 diagonals, A, E, I, B, F, G, and C, D, H. And I'm going to multiply those together, and I will add them. So I'm going to get A times E times I. Well, yeah, maybe I'll just write AEI. So AEI plus BFG plus CDH. And then we go in the other direction. Let's see, I'll use this. So there's these other diagonals, CEG, AFH, and BDI. So we get those diagonals as well. And those backward diagonals, we go in the we go with a minus. So it'll be minus CEG minus AFH minus BDI, like that. So that's those backward diagonals. We get minuses there, and for the forward diagonals, we have plus. So I guess we could do that example that we had from above. So we'll take this 3 by 3, just paste it there. And then I'm going to take the first 2 columns and I'll put them over here. And then I'll highlight. So we get 1 times 1 times 2, x times 2x times 0, x squared times 0 times 0. And then we have the other direction as well. We have x squared times 1 times 0, 1 times 2x times 0, and x times 0 times 2. So what do we get? The Wronskian is going to be 2 plus 0 plus 0. Those are the red, that's the red ones. So those are the red terms. And then, oops, and then we get the other direction, we get minus 0, minus 0, minus 0. And that is the backward diagonals. And again, we get 2. Okay, so that's like, I guess, 2 methods. So we did cofactor expansion. Maybe I'll write that down somewhere. So this first way that we did it was using what's called cofactor expansion. So first we did cofactor expansion. If you want to look that up and look more into cofactor expansion. But what's nice about cofactor expansion is it works for 3 by 3, 4 by 4, 5 by 5. So it works for any size of matrix. And then we looked at kind of doing it just using the first row. And then we saw that using the first column was easier because of the zeros. And then we looked at this other technique that only works for 3 by 3. So I need to emphasize this. This technique only works for 3 by 3 determinants. So it is a nice technique if you're just looking at a 3 by 3 determinant. Okay. So let's look at another one. And maybe, maybe this time we'll use that 3 by 3 determinant trick for this one instead of cofactor. I think we've done enough cofactor expansion probably. So let's show that these three functions are linearly independent. So we'll write down the Wronskian. It's the determinant where we write down those three functions in the first row. And then we take their derivatives. So I'm using chain rule to get those derivatives, and then take the derivatives again. Okay, so what is the Wronskian? What is this determinant equal to? So let's try that new technique that we just learned. So I'll write that down, then take the first two columns and paste them over here. And then we have our forward diagonals. So that's EX 2 e to the 2x and 9e to the 3x. So let's just start writing this down. So we have, well, what is the product of that? So maybe I don't want to rewrite it out. Let's do it in our heads. So what is the product of this? So 1 times 2 times 9 is 18. And then what do we get when we multiply e to the x, e to the 2x, e to the 3x? We get e to the, we're going to add the exponents. So we'll get e to the 6x. Okay, so that's the first diagonal. Then we have this diagonal here. And what is that? 1 times 3 times 1, so we get 3. And then it'll be, again, e to the 6x. And then this diagonal there. That's 4 e to the 6x. Yes. Okay. And now, so that's the forward diagonals. So we get those three terms. And now we're going to do the backward diagonals. So we'll do this way. That is going to be 2 e to the 6x minus, let's see, 12 e to the 6x and 9 e to the 6x. Okay, so there's our backward diagonals. And very fortunately, all of these terms are e to the 6x, so we just have to add up all these coefficients. Okay, so we have to do some arithmetic here. Let's see, I'm just trying to think of an easy way to do this. Okay, so we've got 18 minus 12, that's 6. And then we have, let's see, so we have 6, and then another, I guess another 2 here, so that's 8. and then we have minus 6. So that is going to be that is going to be 2, I think. Did I do that right? Let me see if I can do it in a different way. Double check my calculation. Let's see, what was another way to do it? I noticed there was like a plus 6 and a minus 6. So how would I think of it that way? So we have 21 and then minus 21. Yeah, okay. So 21 minus 21, that's 0. Then we just have 4 minus 2, and that's 2. Okay, perfect. So it's always good to double check your answer. Do the calculation in 2 different ways and see if you get the same thing. So there it is. So there's our Wronskian, and in fact, this is not equal to 0 for all x, but we just need it not equal to 0 for some x. So therefore, e to the x, e to the 2x, and e to the 3x are linearly independent. Okay, so nice. I'm actually glad we did this diagonal trick, because it would have been a lot more work if we were to do cofactor expansion on this example, and we would have got the same answer anyway. All right, great. Let's see. So now that we know those three functions are linearly independent, these 3 functions are actually the solutions of the same homogeneous differential equation. So in fact, all three of these functions are solutions of this it's like a 3rd order differential equation. So this is y prime, so the first derivative, second derivative, and there's the 3rd derivative. So this is an order 3 linear differential equation. It's homogeneous because of the 0. And so we know that once we have 3 linearly independent functions, we can form what's called the complementary solution, which is the general. We can form the general solution of this differential equation. Okay, so let's do that, and then we want to find which general solution satisfies these initial conditions. So because it's a 3rd order differential equation, we need actually 3 conditions, because there's going to be C1, C2, C3. We need to solve for 3 unknowns, so we need 3 conditions to solve for those. So for a 3rd order differential equation, you kind of need like an initial position, initial velocity, and you also need an initial acceleration, and then you're able to determine what's going to happen in the future. Okay, so let's do this. So maybe not the general solution, but a general solution of the differential equation is, and it is the complementary solution, but I mean, we're just dealing with a homogeneous equation, so let's just normally I'd write a C there, but if we're doing a non-homogeneous one, but this is just a homogeneous one. So this is a general solution of this. Okay, so there's a general solution of this differential equation, and we want to find the solution that satisfies these initial conditions. So to do that, we're going to need the first and second derivatives. So let's do that first. I always forget to do that before getting started. So let's just take the derivatives of this function. And once more, it's just like doing the Wronskian, actually. It's precisely that. In fact, that's sort of how we ended up getting this Wronskian, was from this idea. Okay. All right, so now what are our initial conditions? So I think y of 0 was 0, y prime of 0 was 0, and y double prime of 0 is 3. Okay, I'll try to remember that. So let's do this one first. So y prime, or y of 0 equals 0, so we get c1 times 1 plus c2 times 1 plus c3 times 1 equals 0. Okay, y prime of 0 equals 0. We get c1 times 1 plus 2c2 times 1 plus 3c3 times 1 equals 0. And y prime of 0 equals 3. This gives us c1 times 1 plus 4c2 times 1 plus 9c3 times 1 equals 3. Okay, let's write this linear system out. C1 plus C2 plus C3 equals 0. C1 plus 2C2 plus 3C3 equals 0. And C1 plus 4C2 plus 9C3 equals 0. Okay. So I suppose, oops, not 0. The last one's not 0. 3. Okay. So I suppose many of you have a calculator that's able to solve a 3x3 linear system like this. I can also, my preferred way of doing it is using Julia. So maybe I could show you how to do that in Julia. I guess there's other ways of doing it as well. But if you're to do it by hand, I guess we could try to do it by hand, and then we could check our answer on the computer. So let's do that. So that way we can double check our work. So how would you do this if you've taken linear algebra class? Then you know that you can write down what's called an augmented matrix, where you just write down the coefficients of these variables. And then usually you draw like a vertical line to separate it from the right-hand side. And then we do some row operations in order to make this into a simpler form. So what we can do is we can subtract row 1 from row 2. Okay, so it's another way of saying that is we will multiply row 1 by -1 and then add it to row 2. Although we keep row 1 the same, we don't change row 1. So this is just updating to get a new value for row 2. So we're going to subtract this row from this row. So that will create a 0 here. This will be a 1, and this will be a 2, and that will be a 0. Okay, and now we can do the same for the last row. Maybe we could do both at the same time. So subtract row 1 from rows 2 and 3. And this will put zeros here. So it's kind of like we're getting rid of the C1 variable from these other equations. So 0, 3, and 8, and 3. Okay, and now the next step is after I've put zeros here, I got rid of the C1 from equations 2 and 3. So now there's no C1 there. And now I get this like smaller linear system here that just involves C2 and C3. So in other words, we now have C2 plus 2C3 equals 0, and 3C2 plus 8C3 equals 3, because we removed the C1 from those two equations. So you could do this by hand and like write the C1, C2, C3 everywhere, but it's just a lot nicer to work with matrices because you don't have to write as much. Okay, now we want to do the same thing to get rid of the C2 from this equation. So I want this to go away. I want that to be a 0. And that's like taking this equation here, multiplying it by -3, and then adding it to this equation. So let's do that. So now we will, now we're going to multiply, or maybe I'll say it in a different way. We're going to add -3 times row 2 to row 3. Okay, so let's do that. So the first two rows, they're going to stay the same. So I'll just copy that there. And it's just the last row that's going to change. So this will be 0 still, because -3 times 0 is 0, and then add that to 0. But -3 times 1, and then add that to 3, that gives us 0. -3 times 2 is -6. Add that to 8 is 2. And then -3 times 0 is 0. So we get a 3 there. So now this is a really nice linear system. Let's see. So I'm just going to maybe put a little box around, you know, what did we do? So this is what we did here, and this is what we did here. Okay. Or I don't know. I mean, that's what so that's how we got that, and then this is how we got this step here. Okay, so now we're in good shape, because look at this last equation. Now it just involves C3. So in other words, we have 2C3 is equal to 3, and that tells us that C3 is equal to 3 divided by 2. So there's our first value. So C3 is equal to 3 divided by 2. And then this next equation here is C1 plus 2C3 equals 0. So we have C1 plus 2C3 is equal to 0. But we know what C3 is, so we can just substitute that in, and we'll end up getting, let's see, this will be like 2 times 3 over 2, so that's 3. And then I'll just move that over there, and I'll get -3. Sorry, I'm skipping some steps there, but it's just substitute the C3 in over there. So I'm going to do substitute. So I substitute this into there, and I get C1 is equal to -3. Okay, so hopefully that's easy to follow. And then what's the first equation? First equation involves C1, C2, and C3. And we can, again, do the substitution. So maybe I won't go through all the steps, but we get C1 is equal to, oh, whoops, I made a mistake. That's a C2. C2 there. Okay. All right, so now I'm going to substitute this -3 into here, and the 3 over 2 goes there. So we'll end up getting C1 is equal to 3 minus 3 over 2, and that is 3 over 2. Okay, so therefore, y is equal to 3 over 2 e to the x minus 3 e to the 2x and plus 3 over 2 e to the 3x. Okay. So there it is. Okay, well, maybe I won't show you how to do this in Julia. I'm sure you're quite resourceful. You know how to do this on your calculator. And there are other ways to do this as well. But that was the last example I wanted to do today. So that is the end of section 2.2. And that's it. So thanks so much for watching.